Thanks for coming today. It's a pleasure to introduce our seminar speaker today, Dr. Robert Ladwig. See if I can use my limited German there to say that correctly. Robert's coming to us from Aarhus University in Denmark, where he's an assistant professor, and before that did his training at two of the sort of global hotspots of limnology, his PhD at IGB Berlin and the Technical University of Berlin, and then a postdoc at the Center for Limnology in Wisconsin, working with people that many of you know, Hilary Dugan and Paul Hansen. Robert describes himself as a computational limnologist, and I was asking him before the seminar who else he knows who calls themselves a computational limnologist. I can't think of very many myself, but I think it's a really apt description for the work that Robert does. He uses really sophisticated process-based and sort of machine learning models to tackle lots of interesting questions in limnology and aquatic sciences, ranging from salinization to patterns of ecosystem metabolism to, I don't know, lots of other things over the course of his career. He's also been really engaged with a few different sort of leadership groups, sort of synthesizing models and using them for useful things. So he's organized a, excuse me, a sort of coding workshop hackathon called, what is that called?
Hacking Limnology.
Hacking Limnology, thank you. That's been a big force, and especially for early career researchers over the past several years. He's developed a sort of ensemble package for putting together a bunch of different lake physical models to make it easier for people to do model comparisons. And he's a leader of a EasyMIP model intercomparison working group on lake ecosystems. So really a leader in this kind of stuff around the world. And that's probably enough yapping for me. It's a pleasure to have Robert here, and hope you enjoyed the talk. Thanks.
Well. Yeah, thank you so much, Chris. Hi, everyone. I'm really excited to be here today. So when I lived in the US, I always wanted to come to the Carey Institute. So for me, this is like a really big day to finally be here. So in the next 45 to 50 minutes, I want to talk to you or with you about complexity, uncertainty, and sparsity. And I want to engage in a discussion that I think we should, or that I want you to think about, that we maybe should rethink how we want to apply models for aquatic ecosystems. So yeah, so this is just like what I did in the past, which Chris just summed up. So to my PhD, I worked a lot about like lake management and urban, like in cities like Berlin, and how we can improve them. I also worked on applied reservoir management in Japan for a short time, looking at cyanobacteria blooms and how we can mitigate them with different like management options. Then I moved to the US to work with Hilary and Paul for about 5 years, also on different topics like snow, ice, modeling, metabolism, and also lots of deep learning. And then since 2023, I'm in Aarhus, Denmark, at the ocean, working with a really nice group in freshwater ecology. And yes, I describe myself as a computational or more like theoretical limnologist, so I mostly apply and develop aquatic ecosystem models, but not just for the sake of modeling, but also, of course, to further our understanding of ecosystem processes. So I also go out in the field sometimes. I have 3 main research topics I'm really interested in. The first one is about like physical limnology, to understand how, for example, turbulence, microscale turbulence can affect algae dynamics or like biogeochemical cycling. I'm also really interested into freshwater metabolism, especially linking this to carbon cyclings, for example, of methane and CO2 emissions from lakes. And also for the last years, I'm very active in a really nice international group working on knowledge-guided machine learning, so how we can best integrate deep learning into process-based modeling frameworks. I also have a really nice small team in Aarhus, so we have the computational Limnology team. We are currently 3 to 4 people. You can see myself here. This here is Ahmed, my first PhD student who just started like a month ago. And this is Tuba Buchak, who's also working as a researcher on our team. We have 2 main research topics. So one, of course, is looking at ecosystem modeling tools, so to really use these tools to better understand processes in one specific lake, for example. And the other one is also like landscape limnology, to understand like fluxes across streams, catchments, and lakes and ponds. We also do lots of advisory work at our institute for Danish governments, so the Danish EPA, the Danish federal agencies. And here we are mainly working on nutrient limitations, so to identify if a lake is nitrogen or phosphorus limited. Also looking at nutrient retention in lakes, so to better adapt our restoration policies, and in general to inform the government how we can best manage lake ecosystems. For research projects, currently we have two active ones. One is about lake ensemble modeling, so to develop new tools to improve how we can better facilitate ensemble modeling of lakes. And the other one is about how we can best put AI, so artificial intelligence, into ecosystems. And for example, Ahmed Al-Bashi is working in this project. And if you're also interested into deep learning and how we can use this for, or if you know somebody who's interested to use deep learning for lake modeling, I will open up a postdoc position early next year. So in this talk, I want to convince you that now we have the right time to rethink how we approach modeling for aquatic ecosystems. And before I go into this, I have a small recap. So first, I want to talk about aquatic ecosystems. And of course, you all know this, what lakes are aquatic or are ecosystems, which is a relatively new concept just formulated by Forbes at the end of the 19th century. And he demanded that we should really study the entire biotic, abiotic dynamics in lakes. So we can use like a beautiful lake like this one, which is Lake Mendota in Wisconsin. And then we have to put a box around it, right? So now we have an ecosystem here. So we have system boundaries. We know what goes in, what goes out. We have atmosphere, we have sediment, we have rivers. And if we know what goes in and what goes out, we can build a mass balance. We can build an energy balance and also momentum balance. So we can really identify this as a system, as a dynamic system process. But of course, we also have to understand what's happening inside this box. And here it becomes very fast, very complex. So right in lakes, internally, we have many physical drivers. We have heat fluxes, we have inflow entrainment, we have internal waves, and we have sediment shear stress. And of course, they also all affect the biogeochemical cycling. And this also interacts with the trophic food web, so the phytoplankton and the zooplankton. So we have many causally linked processes across time and space. And of course, we also have very interesting seasonal dynamics, right? So we have a very distinct phenology in lake ecosystems. And I would argue that even like physical processes are very distinct temporal patterns. So for example, in physics in lakes, we have the ice formation if the lake is in a temperate climate zone and deep enough. We have spring mixing, and we also have summer stratification. So in the textbooks, right, we have lakes which are stratified if they are deep enough. And we have warm water on top of cold water. This warm water layer here is actively mixing. It's in contact with the atmosphere. And below that, we have this thermocline, so a huge density gradient, which really limits the transport of nutrients from the top to the bottom and from the bottom to the top. And this stratification is really interesting because it will definitely affect also biogeochemical cycling, right? So you can see here an example for oxygen, also Lake Mendota over depth and time. And here the color, so green means it's a lot of oxygen, blue means it's more or less zero, so we have anoxic conditions. And you can see here again, once the lake stratifies, so warm water on top of cold water, we have a strong thermocline, so now we get a depletion of oxygen happening here because the transport from the surface to the bottom is limited. And of course, this can have like unwanted consequences for redox reactions and can also limit the habitat for different fish species. And of course, also the physical processes and the biogeochemical ones will also affect the ecology, so the ecosystem processes. And here's just a simple example of like a typical PEC model for like phytoplankton succession in lakes. So we have the ice formation during winter, then the ice breaks up. We get more sunlight coming in, or more light in general. We get higher temperatures, and then we get the first spring algae bloom, followed by the first bloom of zooplankton. Then the lake warms up, we get stratified conditions. Then we mostly get a cyanobacteria bloom. We also get the emergence of fish species here behind in purple, and the second zooplankton bloom. And then we get like the cold season, so it gets windy, it gets cold, and we get the second diatom bloom in fall. But you can see there are heavily linked seasonal dynamics in lakes. So lakes are definitely very complex, hence non-linear ecosystems with profound seasonal dynamics that are causally linked to each other. And of course, to really understand these dynamic systems, now we need modeling tools, right? So we need the modeling tools to understand or to see if our understanding or how we think reality works can be proven with mathematical equations. So to test mechanisms and also hypotheses. And of course, we always try to strike a balance here for modeling between like oversimplification and over-parameterization. So we try our best to find mathematical tools to really describe these different dynamics which we can observe in lake ecosystems. But are our models really sound enough? Are they good enough for the job? And this is, of course, a very hard question because there seem to be many factors that cause us to have like models that fail to give like best projections for ecosystem dynamics. For example, Elliott Graves said that in all these complex ecosystems, you have all these nonlinear dynamics, and they're always more or less impossible to really model using just partial differential equations. Also recently in a paper by Barbara Hahn, she also pointed out that it seems for ecosystem dynamics, mathematics nor data are really good describers for these dynamics to really simulate them afterwards. So they are not really effective in replicating what we have seen in the field conditions. And also Serraris and Kalutiri pointed out in a review paper some years ago that at least for ecosystem modeling, our improvements are stalling over the last decades. So for the last at least 15 years, our models are not getting better for water quality dynamics. And why is this important? Because right now we're living in a time of change, right? We have climate change happening, we have a biodiversity decline, and we have water quality deterioration. So we have huge global challenges, and we need the best modeling tools to really be up for this job, to really get the best projections possible to inform stakeholders, policymakers, and also managers. So in this talk now, I want to try to argue that we need to rethink our modeling approaches, at least for lakes. And I have three main topics. So first, what's up with our modeling tools? Then do we have the right data? And at the end, I want to argue for a shift towards more like a hybrid modeling approach. Okay, so ecosystems are definitely complex. So now we can go to modeling. And here I have three short stories. First, I want to prove to you that ensemble modeling is really powerful. Then I want to ask the question, is there like a best model that we can use for everything? And at the end, are models really unique hypotheses? And so for lake modeling, it's like a long narrative, but when I started my PhD, I noticed, like many people before me, that there are many, many lake models out there. It's really hard to choose like which model you want to use if you just start aquatic science research. And so the big question is what model to use and also for what reason? Do you just want to use it because your supervisor always used that, or is there like a specific reason to use this one model for everything? And I found many people who are like-minded and who also wanted to investigate this. And in 2018, we had like this first meeting of this grassroots group called AEMs in Australia, which stands for Aquatic Ecosystem Modeling Network Junior. And we met up and we talked about which model to use. And we all decided we have to just run a bunch of them together and really explore what works best. So we really worked on ensemble modeling for the next years. And finally, in 2021, we published this paper and a software called Lake Ensembler. And this R package allows you to run the 5 different physical lake models, so just for temperature, on the same data, so the same input data. It also allows you to calibrate them and everything else to process them. So it really allows you to assess the uncertainty behind your models. And then since 2022, I'm more or less working sometimes together with Tuba Bucek, Jorrit Messmann, and Tobias Anderson on the water quality ensemble modeling. And we noticed that physical ensemble modeling is really easy, but water quality can become really complicated because each model has different equations and different names for the same parameters. So this is like a really slow process. But I think ensemble modeling is really, really powerful and really important to address uncertainty and to explore what is working well and what is not. And of course, the motivation for this, or more like the philosophical rabbit hole from this, comes from many papers before that. So we always knew since the 1990s by Naomi Reskes that models can only be evaluated in relative terms, right? So their value is always heuristic. There's not one model that works best for all cases. The same was argued recently by Wendy Parker, who said that models can never be confirmed, but only to see if they are fit for a specific purpose. So you just can't use any model for any task. Then recently also May said that calibration is always a form of art. So it also depends on the modeler himself or herself or themselves, how they want to approach this. And to bother just this year point out that maybe we not always should argue to use the most simple model, but maybe also have to build more complex models in the future for specific research questions. So the question is, for lake modeling, are our models suitable for the purpose of water quality modeling? Of course, the purpose is here we have complex, chaotic, dynamic systems, and we use now a vertical, one-dimensional model in most cases for them. And here the conclusion is maybe if you only use one model, we could be very overconfident in these results, and maybe we are not really seeing the full picture. So this is why I think ensemble modeling is really cool. And I want to show you like first a highlight or a paper under review by a PhD student, Lipa, who I'm currently co-supervising together with Carsten Rinke here. So Lipa is working at the Helmholtz Center for Environmental Research in Germany. And together with Johannes Feldbauer, Jorrit Messmann, Tua Bucek, Tom Chadwell, and Daniel Mercado-Bettin, we worked on this global paper to use one oxygen model across the globe. And we use many different models combined in this ensemble to really get the uncertainty better. So what Lipa did, he built a really simple oxygen depletion model for the bottom layer in the lake, so the hypolimnion, so just below the thermocline. The model looks like this, so it's just like a change of oxygen depending on the depletion rate, which also depends on your trophic state. So it's really high for a eutrophic lake, it's low for an oligotrophic lake, and the temperature multiplier. And of course, the idea is once the lake stratifies, right, we get these typical depletion patterns happening here below the thermocline. This is all based on the theory by Livingston and Imboden from 2011. And Lipa tested and verified this model for a bunch of lakes in Germany in all these papers. And then he applied this using EasyMIP data. So EasyMIP is this global network of scientists in agriculture, biogeochemistry, hydrology, economics, and lake science to do like global climate change assessment studies. And the cool thing is we have like at least 73 lakes across the globe where we have long-term data to verify models. So now Lipa used 5 different climate models to look at the future conditions until 2100, together with 4 different climate change scenarios, looking at no change in the future until like things are getting really, really dark. Then we also used 3 different lake temperature models just to run the oxygen model, so just to also cover our basis for temperature dynamics. And then he ran this oxygen model on 73 lakes together. And I want to show you the results of that. So these plots show you now like the time to anoxia over time. So how long does it take after the lake stratifies until the lake becomes anoxic? So you can see 3 different lines. So the blue line is like a mild climate change scenario, and the red line is a very extreme climate change scenario. So for example, these are all the oligotrophic lakes. These are just examples of 3 oligotrophic lakes around the globe. This is Lake Taravera, and you can see here now for the extreme climate change scenarios, we start at like 160 days, and at the end of the centuries, we are down to 120 days. So the lake lost 40 days of being or having oxygen available inside the hypolimnion. So oligotrophic lakes become more anoxic. Then for mesotrophic lakes, you can see here Mount Bold, again, starting with 85 days, going down to about 65 days. So again, you lose like 20 days of anoxia of oxygen in this lake in the future. And of course, for eutrophic lakes, it's a bit more extreme. So they always start mostly below 100 days. If you look here at Lake Mendota, you had at the beginning about like 75 days. At the end, you have like 65 days needed until you reach anoxia in the whole hypolimnion. So you lost 10 days of oxygen being available for anything below the thermocline. So globally, Lipa could show that lakes become more anoxic in the future. You can also see like the range, like the shaded color behind all these projections, and this shows you the uncertainty. So with the help of these ensemble modeling tools, which are very cheap and very cost efficient to run globally, we could also address the uncertainty due to climate change scenarios, climate change projections, and different lake models. So it's a very powerful tool to really use ensemble modeling just to cover the uncertainty or sensitivity to future processes. And then the next question is about which model is now the best one. So we can use ensemble modeling, but maybe there is like the one golden model behind it, the one model we should always use. And this was a study just published this year in Hess, also led by Johannes Feldbauer with Jorrit Messmann and Tobias Anderson. And we looked now at this question, right, this model intercomparison study, so to find out which model is the best. And the results of this study were the basis for LIPA's global modeling framework. And this was just like to get the temperature modeling better. So the idea was just to do like a simple model evaluation just for the physical dynamics of temperature modeling. And for this, we used 4 different one-dimensional vertical lake models. So they always have like this equation. So it's some kind of reaction diffusion equation for temperature. And they always use like atmospheric boundary conditions to produce like a temperature profile. And we also ran them on 73 lakes using the EasyMap data across the globe. And I now want to show you the results for the fit, the performance of these 4 models. And these are the results for all these models together after calibration for 4 different performance matrices. So this is the bias. If it's close around 0, this is a really good fit. This is the Nash-Sutcliffe coefficient of efficiency. If it's above or next to 1, it's a really perfect fit. This is the root mean squared error, so the lower the better. And this is the R, so also the higher the better is the fit. So you can see like these different performance matrices, and most models have a really good NSE above 0.8 and a really low RMSE, always mostly about below 2 degrees Celsius. So in general, temperature modeling is really powerful to replicate the observed dynamics. But you can see these small pie charts. And these pie charts show you a color for each model whenever it was the best model for a specific lake. So for one of these 73 lakes, whenever this model was the best one. So you can see here, at least every colors are for every plot available. So for every performance matrices, at least one lake model was the best model for a specific lake. So there's no winner that always had the best projections across all these 73 lakes. If you look at the NSE, then for 42% of the lakes, SimStrat was the best model. If you look at the bias here, you can see the pink model, GLM, was the best model for 47% of the lakes. So there is no clear winner. I mean, it seems like SimStrat at least mostly was a good choice, but for at least a couple of lakes, a subset of lakes, also the other models produced the best results. So each model can be the best one, and it really depends on the model itself and also on which metric you want to evaluate for performance. Okay, so there is no clear winner, but still ensemble modeling is really powerful to cover your bases. And this leads me now to say that, again, there is no winner. It's very powerful, but we have to really look at this adequacy for purpose, which I can echo from the Parker paper, saying that we really have to evaluate which model we want to use for a specific lake type or specific modeling purpose. Okay, and this leads me now to the next small story, and this is a paper I'm currently writing up again with Jovet Messman, Tobias Anderson, and Tuba Buchak. And here we want to explore really again, are we overconfident if we only rely on one specific model outcome? And for this now, we only modeled one lake, Lake Mendota in Wisconsin. So it's a eutrophic lake, it's 25 meters deep. And we applied now 3 different water quality models on this lake. So really models that looked at oxygen, nitrate, phosphate, ammonium, silica, 3 different algae functional groups, and so plankton. And we tried to have like the same conceptual framework for all these 3 models, which was quite hard to implement. And then we also tried to use the same calibration strategy. So we always use a differential evolution algorithm. And the idea was to see if our projections are really equifinal. So we hope to see that it doesn't matter which model we run, at the end they will all give similar projections and be more or less the same outcome. Even though we have seen for temperature, some models are better, but we thought for water quality, because it's more complex, maybe they all will at the end average out to the same. So I want to show you the first results. These are like the performance across states. So this is just for temperature. You can see 3 plots here. So this is like the residual over depth. So if it's close to 0, it's a really good fit. You can see the 3 different colors here for the 3 different models. And the uncertainty is behind the range over time. And you can see like 2 horizontal lines here, one at 2 meters, one at 12 meters. So this is about the thermocline. And you can see the corresponding time series data. So here for temperature over time. And you can see again the 3 model lines, and the black dots are the observed data. And you can see if you just look at temperature time series data, all these models seem to do a really good job, right? It's really hard to say that one model is better, and they all have a really good fit for temperature. But you can see here some models have a higher uncertainty close to the thermocline, and definitely the range of uncertainty, so like the shaded area, is increasing if you go deeper in the lake water column. If you look at oxygen, again, you can see, if you just look at the comparison to the black dots, they all have a really good job in replicating like the seasonal like peaks during summer. So just like when we have the algae blooms happening, and also like this really strong depletion happening here in the bottom layers, right? So that all these models are at least able to replicate seasonal dynamics. If you look at the vertical plot, you can see some models have a really higher uncertainty here below the thermocline, but still they're all really close to zero. If you look at nitrate, now things become a bit different. So you can see all these models have an offset to each other. So they have different nitrogen algorithms, equations included. But if you look at the time series data, they are also rather chaotic some points. So some models capture them, some don't. It really depends on the year-to-year patterns. For phosphate, we can see in the surface layer, we have a strong depletion of phosphate happening, which all the models more or less can replicate. But also at the bottom, we can see like the release happening at the end of summer stratification. And at least for the vertical dimensions, they all follow the same pattern. So they seem to have like similar equations involved here. So it's really hard just looking at these plots to identify which model works best for all these water quality variables. And then I try to look at the different fluxes over time. And of course, looking at fluxes in these models is a challenge because it's really hard to extract them because of different equations used. So what I did here, I will show you different plots about two states compared to each other, which are scaled between 0 and 1. So here we'll see like the comparison or the relationship of oxygen to phosphate, both scaled to 0 and 1. Here between zooplankton and chlorophyll A, and between ammonium and nitrate. And here we'll just see a different time series plots, also all scaled. And I just want you to pay attention to like the coloring of these plots to see which model covers which space in these dimensions here. So we are starting this now, so you can see like the relationship, right, for the same input data for all these three models, and which dimensions, like this two-dimensional space, which space they can occupy in their modeling. And you can see here, at least for the first one, oxygen against phosphate, that the pink model at least has more cyclic behavior, so it goes up and down. The green model mostly stays up to here, so it doesn't really leave the space at all. And the pink model mostly goes like covering this. The same for chlorophyll A, so plankton. The pink model has more like this periodic cycles. The purple model is mostly going up and down, and the green model mostly stays in this lower space here. It's more extreme for nitrogen. You can see the pink model goes all over the two-dimensional space. The green model is only producing like this plus sign more or less, and the purple model mostly goes up and down again. So all these models, even for the same input data and the same conceptual configuration, have different relationships between different states here. And they're really painting a different picture because they have different fluxes involved. So it seems to be that the model choice really gives you different fluxes, different processes, different transformations over time. And we wanted to quantify this a bit better. So what we did, we built a small machine learning tool to explore that. And here I just integrated every concentration, every state over the water column, and then I just quantified the first difference between time steps. So it's kind of an approximation of the fluxes of, for example, temperature, chlorophyll A, oxygen, nitrate, and some more. And then we put all this data into a machine learning model, in this case, an encoder-decoder framework. So we got this latent space representation of our input data. So it's similar to like a PCA. So it's like space without real information, but it tells you how it's clustered inside that. And then we took this out and we ran this discriminator machine learning model. And this model had the only job to say, oh, I got a point here. Does this point belong to this model, or this model? Or is this time series belonging to this model, and this model? So the idea was if this discriminator had a high accuracy, this means that this specific model had a really distinct patterns over time. So it was more unique than the others. So not saying it was better, just saying we had distinct behavior in this model, and this discriminator had an easy time to quantify that. And we tested this like this. You can see now the accuracy over different variables which we included. So if we only included temperature data inside this approach, you can see the accuracy is kind of low for these models. So for the pink model, where the chance is about 0.25%, right? So it's a low chance to really identify this model. If you have the purple model, it's about like 50%, and the green model has like 75% chance of being accurately being identified as the right model. And this makes sense because for temperature modeling, all these algorithms are more or less similar, and especially like these two models have more or less the same temperature reactions inside. But once we added nutrients like phosphate and nitrate and temperature to this modeling approach, you could see now the accuracy jumped up. So suddenly they have really distinct time series behavior. If we added then also like minor nutrients like ammonium or silica to it, they were more or less at 100%. And once we added chlorophyll A, so plankton oxygen, it's always 100%. So once we give them all ecosystem states, then this modeling framework always had an easy time saying, oh, this time series comes definitely from this model, from this model, or from this model, meaning they're all like really distinct projections of reality. Okay, so summing this up. So I think models are very uncertain, especially by using only one model. Your model is always your hypothesis, right? So models are definitely not equifinal. So saying you can just use any model and it gives you about the same projections as the other is probably not true, because these models will give you distinct projections depending on which model you are using, right? So your hypothesis, more or less, you think this model is really working and how you think your observed system will work. Then also, of course, the modeler is always a hypothesis, right? So it really depends on the experience of the modeler, which algorithms they are using, which parameters they select, and also when do they stop, right? What's good enough for a calibration? And at the end, also, it's really hard to compare modeling tools. Do you either want to have like sound equations that make physically sense, or do you just look for excellent performance? You don't care. You just want to see it's as close to observed data as possible. So at the end, I think if you're only using one modeling tool for the job, you're more or less overconfident. So you always should use ensemble modeling tool. If you have no specific reasons to just use one model, it's always better to use ensemble modeling to really cover all your bases and to better quantify the uncertainty, because at the end, the models are definitely uncertain. Okay, so ecosystems are complex, models are uncertain, so what about data? And here I want to highlight two PhD theses, which we are currently having in our department. One about everywhere metabolism, and the other one about high-frequency mixing. And of course, this all comes from the fact that I'm mostly using one-dimensional ecosystem models, so only looking over the vertical axis. But of course, our lakes mostly look like this. So this is Lake Raven in Denmark, which is my current monitoring lake. We have like this really deep side over here. We have this small lake mountain over here, and all this really shallow littoral area here in the shorelines really affecting the lake. So it's a very complex bathymetry. It's not easy to say that a 1D lake model, even though it really gives you averaged assumptions over the horizontal axis, will be a good fit for like this bathymetry or this hypsography. Normally, we only have one buoy here, so we only get data at a single point, the pelagic monitoring more or less. And if we are lucky, we also have a buoy with different probes over the vertical axis, but we will still get only data at one point, right? Which can be a bit maybe biased for like a real bathymetry. So just to show you how biased we can be, this is an example which a colleague of mine, Tom Davison, was doing in 2020. This is like a short campaign for greenhouse gas fluxes. This is Lake Omstrup, also in Denmark. And what Tom did, he deployed several different floating gas chambers to measure greenhouse gases across the lakes, across 4 gradients, so one gradient here, one here, one here, and one here. And normally our buoy in the lake is, of course, here. This is our buoy, which represents the whole lake dynamics and how we understand this lake ecosystem. But as you can see, at least for greenhouse gas emissions, it's very, 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 very variable. It's a huge heterogeneity in emissions happening here. There's a huge gradient happening here, and there's also like a huge emission happening next to a macrophyte bed near the shore. So definitely it's important to pay attention more to spatial variance. But this is also true for temporal variance. So this is high frequency data, which also Tom has collected for this Lake Omstrup. So you can see high frequency data of temperature on the x-axis over oxygen on the y-axis. And you can see this now across a year. So you can see like the color here, or like the color is changing across different months. And the red line represents an oxygen saturation of 100%. So if the dot is above that, we have higher production. If it's below that, we have higher respiration. And you can see here for the high-frequency data, this is like very erratic, it's very stochastic. So it goes up here in March, we have the spring algae bloom happening, then here it dips down a bit in April, and then in May, June, we have these huge cyanobacteria blooms happening, so also it goes up, up, up again. And then Danish lakes are very shallow. So most lakes are like 5 meters deep, also Lake Omstrup. You can see here in July, the lake is stratified for certain conditions, but then we also have mixing happening. So suddenly also the oxygen goes down again, and it seems we have like higher respiration. Then we get October, November, the lake becomes more calm, and now we end up here. But you can see high frequency data really paints a really interesting picture about lake dynamics and can really beautifully underscore the variance happening here. And this is really important to think about high frequency data and also to think about how our models can capture that. And this is now results by Bennett McAfee, who was working with Paul and me together in medicine. And Bennett used an oxygen model and compared this to observed data, also for Lake Mendota. So you can see oxygen observed in blue against oxygen modeled in the green line here. And it more or less seems to capture at least the daily fluctuations. But then Bennett looked at the power spectrum. So he looked at the power spectral density behind this time series data. And of course, it's a bit more complex, but I just want to show you this is the observed one, this is the modeled one. And you can see these orange lines are like the same gradient in both plots, just to give you some kind of reference. And all these two time series have the same power spectrum peaks, so at a year, 6 months, 1 month, 1 day, 12 hours, and the same peaks also here having the model data. But once we come to the high frequencies, so across here you can see the model suddenly can't replicate the same power spectrum as the observed data. So it has less power over here, meaning that our models really fail to capture the real intensities in these high frequency fluctuations. So it's really important that maybe we should really build better modeling tools to look more at sub-daily time steps. But for this also we need to get more high frequency data. And this is currently the job of 2 PhD students. This one is Edward Danielson, and he works together with Tom Davidson and Torben Lauritsen. And Edward really wants to look at methane gas emissions and oxygen dynamics in Danish lakes. And for this, Edward had a really cool project just like this fall. So he called it swarming the lake with everything we have, more or less. We put every equipment we own on a single lake. So what Ed did, he looked at 4 lakes in Denmark, and for 2 to 3 weeks, he put every equipment we had on these lakes to really capture the whole spatial variance and also the temporal variance. And he really wanted to look more on oxygen and the carbon balance. And for this, we used our home-built low-cost gas chambers here for methane and CO2. We also deployed our homemade buoys, which looked like that and which are not that stable, so they won't survive like a flock of birds settling on them. We also deployed our real buoys on this lake, and we also deployed some ATCPs, which are acoustic Doppler profilers, to better measure the velocity happening inside these lakes, so to really see if some mixing is happening also over the horizontal axis. And then he put this all on one lake for 2 to 3 weeks. This is one Danish lake. You can see we put about 15 floating gas chambers on here, several buoys, and also the ATCP. And I really want to show you some first results of Ed's work, but he's still in the data crunching process. So hopefully by next year we'll see how the whole swarming of lakes can really reflect better high frequency and spatial variance. Another project is also done currently by my PhD student, Ahmed Al-Habashi, together with Tuba Bucek and Tom Davidson, and he's looking more into how we can use high frequency data with machine learning. And for this, we want to, Ahmed is currently starting a long-term monitoring at my Danish lake, Lake Raven, Raven Lake, and we want to deploy 3 buoys here. So there's 1 buoy here over the depth, 1 buoy here, 1 buoy here, and also 1 profiler that always goes up and down 3-4 times a day. And we also want to take weekly water quality samples and also weekly profiles of turbulence. And the idea is to get all this data to really look at 2 distinct processes. One is we have a really nice deep chlorophyll maxima in this lake caused by dinoflagellates. And we want to understand better what's really causing them, because they are there every year at the same depth, but so far we never really noticed them before. And we also have really nice stable stratification in this lake, so we always have a daily thermocline and also a seasonal thermocline in the depth. So we really want to explore this further. And so currently we're looking at measuring turbulence and getting used to it. So we have these ATCPs deployed, and these are the turbulence profilers. And you can see myself here trying this for the first time. So currently we're getting trained in that better. But the idea is to get all this high frequency data. So a huge data set with high frequency data, some snapshots like weekly sampling, and to use this with machine learning methods to get better equations for turbulence and algae growth. So the main idea is to have all this noisy data, denoise that, and then use some kind of really clever equation learning to see if we can find better parameterizations for turbulence and phytoplankton just from high frequency data. So yeah, data, I think, are definitely biased. So in space, we mostly have like this pelagic monitoring paradigm. So we have limited coverage, and we don't really cover this horizontal exchange. But we need more spatial data to really understand mechanisms better. In time also, if we only sample like bi-weekly, then we definitely either underestimate or overestimate the fluxes, and now we need more high-frequency data to better identify which of these extremes it is. And also our models definitely underestimate high-frequency dynamics. So currently we are changing our Danish monitoring, at least for some lakes, so we really want to, in the future, deploy more low-cost loggers and more homemade buoys on many of our lakes, and we really hope that over the next years, we can release all this data as fair data to everybody outside. Okay, so ecosystems are complex, models are uncertain, and data are sparse or biased. So what can we do? And I think the best way to tackle this is to use a new paradigm called knowledge-guided machine learning to reshape our concepts. And currently, we're working on a perspective paper to wrap up or to sum up what we did over the past 10 years, more or less. And this is led by a lot of people here from UW Medicine, Virginia Tech, Pittsburgh University, Alabama University, and also at Aarhus University. And I just want to highlight the role of Anushka Patne and Kaylin Carey, who are both faculty at Virginia Tech, and also Paul Hansen, who's at UW Medicine. But so the idea is here, right, that we have in ecology, we have mostly a theory-driven science of decades of knowledge, which we should really utilize better. But we have these complex systems, we have powerful but ill-posed models, we have bias and limited data. And of course, models and data are always incomplete representations of a real system, but still we can use them maybe to build better modeling tools to get better upscaling on the global scale. And of course, for the last years, artificial intelligence is a big topic, right? Because these models can easily learn very complex features from real data without knowing the truth. So they're really good in discovering these hidden dynamics behind the data. But of course, they also have big challenges. So they're really bad in like generalizing outside of the training data. They also mostly are described in most cases as black box models, so they're really hard to interpret. And because of that, we have limited control of using them for scientific research. And before I show you how we want to change that, just as a small recap, so for statistical modeling, right, it's mostly going from data through an algorithm to gaining knowledge, simplified, of course, but like as a general approach. Then for modeling or process-based modeling, we have like knowledge, you build a new model and you get predictions and also hopefully knowledge about to see how your system of equation understands reality. And for typical machine learning, you use lots of data, you run them through an algorithm, and then you also get better predictions. But now we have this new paradigm called knowledge-guided machine learning, also like physics-informed machine learning, where the idea is we really want to integrate our empirical knowledge or process-based knowledge with a deep learning model. So something like this, right? So we have now our expertise, our scientific expertise. We put this into a modeling tool and into a deep learning model. We put the data into a deep learning model, and we also update this deep learning model with our process-based information to finally not only get better projections, but also to gain new knowledge, new understanding about how ecosystems work. And the main question is always, how can we put in this scientific expertise into a deep learning model? And here there are different approaches. For example, you can look at the loss function in the deep learning model, on the architecture, how it learns, or also how you train the model. And this was done really successfully for temperature modeling in the past, where we have shown in different studies here that once you combine knowledge with temperature modeling can really improve the performance compared to normal process-based models or machine learning models. And mostly we put the knowledge in here either by telling the loss function of a deep learning model that it always has to account for energy conservation, or it can't just like violate density over the water column, or we just first pre-trained the model with like our process-based data, so saying this are our simulations, please or try to learn the real physical equations, and then we train it for our observed data so to get the best out of both worlds. But now we want to use this also for water quality or for ecology. So the goal we are having as a group right now is that we want to use the power of AI by still keeping ecology as the discipline that it is right now. So be adaptive and theory-rich. So we put out 3 or 4 goals for this, which are not new, but which we think are really important for future modeling for ecology. The first one is always we have to leverage our current knowledge to improve our predictions. Then we also have to incorporate multiple scales of variability, so temporal and spatial, across the globe, across regions, across continents. We also have to retain and transfer knowledge, so we can't just learn a new model every time, but we should keep what we had in the past. And we also want to update our ecological understanding. So the idea is, while we have an ecosystem, and we want to now incorporate data and knowledge into a machine learning model. And there are many creative ways to do that. And I just want to highlight you 4 examples from the last years. How we did this in the past, how to build these new eco-KGML models. And the first one is the knowledge-guided training objectives, which is our bread and butter over the last years. And the idea is relatively simple. You have your real lake ecosystem, for example, of observed phosphate concentrations, and then you derive first principles. For example, saying that the change of phosphate from one time to the next can't be so high, can't fluctuate too high, and then to integrate this into the loss function of a machine learning model. And this can really improve your performance and also lower the black box behavior, and was done really successful for phosphorus and for oxygen modeling in the past. And this definitely accounts for the first aim, so to leverage our knowledge while improving predictions. The second one is modular compositional learning, and the idea is here you have a process-based model of different modules, and you can replace now an uncertain module inside an uncertain algorithm with just deep learning. And then you have a hybrid model where you have like deep learning talking to process-based counterparts. And the idea is that this can improve the projections, but keep the whole process structure. And I have shown this recently that this works really well for temperature. And Bennett McAfee is currently working for this on carbon dynamics. And this definitely also applies to the first goal and the second one, so leverage our existing knowledge and incorporate different scales of variability. The next one is inspired by ecology. It's called intra-model evolution adaptation. And the idea is also a bit simple. So you have oxygen dynamics in lakes, and you run many process-based models on that. So different models for deep lakes, for shallow lakes, for eutrophic lakes, for oligotrophic lakes. And then you have an AI behind it that just adapts these model structures over time. So it can change parameters over time, it makes them dynamic, and they can learn from each other. So the AI is more or less controlling the process-based model behavior to make sure they really work better over time, over different scenarios, and they stay nimble. And this was done also in a really good way for oxygen modeling. And this also now applies for the second and the third aim, so to incorporate different scales and also to retain our knowledge. And the last big project we are working on is foundation modeling. And here the idea is we want to have a knowledge transfer from well-observed to data-sparse systems and still improve our projections. The idea is we have lots of lakes here, we run many process-based models, and we use the observed data and the process-based model data to pre-train a deep learning model. So this model gets a lot of data from lakes across the globe, and then at the end we only want to fine-tune this for a specific question, for a specific lake site, to just see if we can utilize knowledge from many lakes for specific lakes at the end. And this was done in a really successful way for oxygen and also for general water quality this year by Abhilash. And this directly aligns to all the 4 goals that we had for eco-KGML. So I really think that this eco-KGML is a good first option to tackle complexity for the future, because at the end, these hybrid models are more flexible than just pure machine learning or pure process-based modeling tools. So hopefully they are not all wrong, but they can really improve their weaknesses by having the best of both worlds. Also, this really helps us to make models more dynamic and more adaptive over time, because now they don't have this rigid model structure, but actually can change them over time if you put more data into it or more knowledge. And also at the end, you can really inform these models by using population-level information from many lakes. So you can use many lakes to inform them to learn better about trophic web conditions and dynamics, and also like biogeochemical cycling. But still, we have lots of work to do to better incorporate spatial information into these modeling tools. Okay, so summing up this whole talk, so I think we should probably push to new aquatic ecosystem modeling tools, because ecosystems will always be complex. And we really have to embrace uncertainty by modeling, by using ensemble modeling, because maybe even though all our models are ill-posed, they are still unique hypotheses, so they still give information how reality should work under these assumptions. Then also we probably have to rethink how we monitor lakes in the future to really tackle sparsity in space and time, which will also hopefully inform for better modeling forecasts in the future. And maybe we have to really embrace more hybrid model solutions in the future to really better merge AI with knowledge to also get more information out from these model projections. And at the end, I really hope we have some kind of this tool in the future. So we have like our human scientific knowledge. We run many ensemble modeling tools. We also run lots of data in space and time. And then we feed this in a creative and flexible way into a machine learning model to get the best projections and also to learn from all these different sources of information. And first, I really want to thank my wife, who is currently doing the hard job at staying home, watching out for the 2 kids. I also want to thank all of you for being here today. If you have more questions, this is my email address, so feel free to email me also after I'm done here. Also next year, if you want to learn more about data science in Limnology, we will do a session at the ASTRO meeting in Canada. If you know somebody who wants to work on machine learning and lake modeling, I will open up a postdoc position. I also want to thank my 2 funding agencies. One is the Aarhus Universitätsforschungsfonds, and the other one is the Willem Fonden. And I also want to thank all my partners at Aarhus and also my key collaborators across the world. And thank you for your attention.
Thanks, Robert. We'll take questions for Robert. Do you want to go ahead and call?
That was a great talk. I have a question about your project where you were looking at the time that it takes for lakes to get to anoxia. And then I saw that under the most mild climate change scenario, some lakes were kind of flat, while other ones were going down with the other extreme cases. So I was wondering if you knew why, and how can you use this information, or someone can use this information to inform policy.
Okay, so the question is, I have to repeat the question for the online audience. So the question is why some lakes retain oxygen, even.
Well, they didn't become toxic.
Yeah.
Yeah,
I can't go back to the slide, but yeah, it's a really interesting question. So that was so the question is why oligotrophic lakes or some lakes just didn't get anoxic over time. But the information on this graph was the time to anoxia. So the time to anoxia stayed constant. So they still became anoxic, just the time didn't become less. So they didn't accelerate their consumption over time. They still became anoxic lakes, but it just didn't increase. The reasons for that is mostly because I guess certification duration became longer for these lakes, maybe, but the consumption rate didn't really account for that. So still the consumption rate was not too high to really accelerate the whole depletion of the hypolimnion for these specific lakes. But this is also because it's just an ensemble average. So there could be some cases where the range goes down a tiny bit for specific scenarios, but we can't really see this because we just average these 5 different climate models, 4 different scenarios, and then all these lake models together. So there could be specific cases for individual combinations where we actually have also an increase of anoxia for some of these lakes, but maybe some of them just stay constant because the climate factors like the wind speed, they don't change much, and maybe in this specific case, the certification duration also didn't change too much. If this answers the question or.
Yes, but can I say something else?
Yeah.
Is there anything different from these old lakes that make them behave differently?
That's a really good question. So right now, I think LIPA didn't look into specific lake behavior, so we tried to calibrate. So the question is why these lakes are different or what makes them different to the others so they don't change too much. Actually, we don't know yet. So LIPA didn't look into specific lakes per se. My guess is that just mainly because maybe the climate change scenarios for these lakes for certain aspects were not as extreme as the others. So it's just the certification duration, which is one of the main factors for anoxia, maybe only changed by a couple of days for the future scenarios and not a month or so. And I think this then will have a huge impact on how fast the lake can deplete oxygen. Yeah.
That's great, Robert. Thanks. 2 questions. One is when you're talking about comparing models and also KGML, are you explicitly looking at how our hypotheses might change? So it's kind of MLKG or some of these model shootouts. Thinking the feedback to what it is that we don't understand about the system in comparing models and what that might reveal. So going beyond just providing our knowledge back into an AI system, what is it that we learn
Yeah.
about what we notice?
Okay. Okay, so the question is, what can we learn by running like a hybrid modeling tool? Just not putting our knowledge in, but also what can we gain out? And that's exactly what Ahmed is currently working on. So we want to get all this high frequency data, and then we want to run this also with process-based modeling tools, and also hopefully with an ecological tool. And we want to see if we can also like use machine learning to maybe find a better equation from our data in the first place. For example, for how we parameterize the turbulent transport over the water column. And then we want to use this equation to test this also against the process-based modeling tools and how we normally envision lake models to perform for turbulent transport. So Ahmed is currently working on using machine learning, also some kind of deep learning techniques to really extract like maybe at least for this lake-specific equations, which hopefully can test also for other lakes in the future to see maybe that turbulent transport could be parameterized depending on different parameters inside what we have measured already. Because normally for these 1D lake models, all these equations are very empirical, especially for turbulent transport. And we really hope that maybe we are just missing some high frequency data to get a better equation out of that at least for most lakes could provide better performances.
Yeah, and I was thinking a little bit more explicitly about what it might tell us about what we don't understand ecologically. So it's kind of feedback loop to code. We thought the system worked this way, but in fact, we must be missing something big.
Yeah, that's a great question. So the question is, right, what is like the surprises, right, behind what we see like in these modeling tools? And we had the same thing for lakes in Virginia, next to the Virginia Tech, where we used also like different deep learning tools to model specific lakes. But we have seen that if we used lakes close to each other, and just to see if we can train the model on this lake and just predict performance for the next lake next to it, this was normally not the best predictor. So we were totally surprised by that. So this didn't really work well. But once we added more lakes from far away regions to the mix, then suddenly also the model became really good in predicting performances for this one lake neighbor next to this one, which was a total surprise for us. So it's really showed, at least for us, that if we learn from population dynamics of lakes, so like many different lakes together, this definitely has a lot of information that we normally don't see, but definitely helps us even to predict lakes that seem really similar, like very much the same next to each other. So we can't really explain why this is the case yet, but this was something we learned, and we really hope with this foundation modeling, once the model is up and running, so using all the data from a bunch of lakes across the globe, that we can really explore these questions further to see what is like the basic information we would need to predict a specific lake in the future. So is it enough to know this lake is deep or shallow or lots of agriculture around it? What is like the basic thing we really need to know to make a good first guess for a lake? And to see how much information actually needs to be provided afterwards also.
So you work with managers a fair bit. What's the kind of one-line answer to the question about what should we do about modeling our lake to make management decisions?
So the question is, what should we do for managers to use modeling tools to restore lakes better?
Yeah. What's your advice to them about what they should do?
It's really a hard one. So we work a lot with like the Danish EPA and Danish government agencies. And normally, of course, they want to get more like an easy, straightforward number answer to be used for like daily management regulations. But we are trying now to really embrace uncertainty more, which is really hard to commit. My advice is always like, if one sentence, that's like really hard. But my advice would be that models should be handled with caution, and you have to pay attention to the assumptions, but they can give you a right trajectory. So they can also provide you like something that is at least based in reality. But don't trust the model 100% if you don't know the assumptions behind it. That's probably 2 sentences.
We won't hold you too much to one sentence. I'm going to jump in with a follow-up question online to one of Kathy's questions. This is from Barbara Hahn, who asks, I was wondering whether, and this one you won't need to repeat because people can hear me.
Okay.
I was wondering whether you have a sense for the degree to which predictive outputs from lake-level physics-informed machine learning models vary based on biota. For instance, the plant or organismal diversity in or around the lakes. And this is maybe related to Kathy's question about whether model outputs might update our hypotheses about processes.
That's a great question, and I have no idea. I mean, we really want to find out right now, right? Because we have like this swarming of lakes. So we really want to find this out, but right now we mostly have only like one data point per lake, like one sample at the depth over the vertical axis. So we don't even know what like the spatial heterogeneity is in most of these lakes. We also want to put more remote sensing to really capture more like these macrophyte beds. But right now, we don't know how this interacts there. I mean, there are like studies showing that biota is definitely very important. So we have seen for our Danish lakes that the greenhouse gas emissions next to a macrophyte bed are very different compared to like the deepest lake side. We also have seen that on our very shallow systems, there's a lot of horizontal flow happening. So definitely production by biota at different sites will also influence the signal we measure at the deepest side. But right now, we can't really quantify that. And hopefully someday, either with a clever machine learning approach or with a 3D model, we could at least try to look into this. But right now, we don't know.
Thanks. I think we maybe have time for one more quick question. I thought I saw one more hand up. Robert, do you want to?
You had your hand up earlier.
Sure. Really, really interesting talk. The integrated modeling approach is really cool, and it presents challenges and also opportunities to maybe address those. You mentioned really sparse sampling. Often sparse sampling is also very biased, just how we operate. That could really affect how the machine learning approach in the integrated model works. But if you understand those biases, you can produce simulated data to test what those like bias effects are. Do we know the biases in these systems and how we sample, and could that be addressed in this approach?
Okay, the question is, do we know like the biases for data, how they affect like the modeling tool, like machine learning, or like our fluxes in general?
Basically, yeah.
Yeah, I mean, for the methane gas emissions, we could show like in a paper by Tuba Buchak, which is currently under review, that definitely if you only measure like monthly greenhouse gas fluxes, we probably have a really strong bias to the real flux. So we had like, what we are currently doing is like 4 hours measurements of greenhouse gas fluxes, which is already not high frequency, but still more high frequency than like a month. And we could show that this definitely had like lower fluxes in general. So different peaks of flux also over time. So definitely if you have more measurement data, more high frequency measurements, at least below like sub-daily, then you definitely can capture better like the mass balance of like carbon emitting from the lake in total. And there is a huge bias because currently we had other studies across Denmark, across Europe with like very uncertain fluxes where like the whole emission of methane is more or less the same as like the uncertainty behind that, like the standard deviation, right? So we really hope if we have better high frequency data from many lakes across the whole world, we can better capture like this uncertainty. For machine learning models, yeah, it's really important that we know what we put in, what we get out, right? And definitely the data we put in can bias the projections. And that's why it's really important that we always put like the knowledge in first, right? So either we restrict the loss function or we restrict how much it can learn. So it always has to use some kind of thing which we trust more, like our process-based mechanisms behind that. And then I think even the bias data at least is somehow controlled. But of course, there's a lot of experimentations and testing different designs. And like in these 4 examples I have shown, it's always like, you have to really experiment around to see what works best for many lakes, many specific research questions, and how much data can control the output. Yeah.
Okay, we're a little past noon, so I think I'll stop us there so people can eat lunch. Robert will be over in the lunchroom, so if you have more questions for him, please join us and chat with him a little more. And please join me in thanking him again.
Thank you.